All right. Well, thanks. First of all, thanks to our speakers for this first day. It was a wonderful set of talks, and really just great to see the exciting work that people are doing around this topic of uh, safety and autonomous systems when we're looking at kind of this modern perspective of learning, of integrating perspectives from people interacting with autonomy, about policy issues. So what I did throughout the talks was I was taking notes, and then I tried to, this is by no means exhaustive, but I tried to assemble some of the points that came up into a set of themes. And I wanted it to all fit on one slide, so we could just sort of keep that there and have our discussion. There are things missing, and let's bring those up during the discussion. But I sort of brought out some common themes that came up in some of the talks. So these are listed in bold here. So the concepts of specifications and certifying specifications. So everybody in their talks talked about this, and kind of going through the talks a little bit in chronological order of the way we did it, or I guess I've moved things around a bit. So for example, in Daniela's talk, she presented in one of the projects she presented the concept of risk level sets and game theoretic frameworks which employ these risk level sets. And as one learns more about, in the autonomous driving scenarios, one learns more about the human drivers around the autonomous vehicle, one can update this, how, this concept of risk, and then update these risk level sets. Lars, in his talk, the specification. So his specification in the landing problem is a landing ellipse. And it's how one designs the models and then captures these diversions and is able to kind of shrink those so that the system lands within the specified region, is posed as a convex optimization problem. But the really exciting thing there is the kind of the certification that he was able to use with this idea of lossless convexification. So what does that mean? That no region of the feasible space is removed in the convexification. So there's a kind of certification built in there too, when you go from the original problem specification to its convexification. Hadass spoke about, in terms of specification, she spoke about levels of specification, and in particular, how one uses feedback in those levels of specification. So she talked about logic level specification, and then feedback here is information that can help you fix the system, for example, to update those specifications. Sandeep, in his talk, he said it quite bluntly, right? Data is the specification here. When we're looking at problems like the one he showed from Xenophon Koutsoukos at Vanderbilt with these non-conforming measures, so asking whether or not the data that you're receiving to be processed by the learning-based component, a neural network, you're asking whether or not that data is in distribution. Is it in the distribution of the data that was used to train the learning-based component? So here, data is the specification. We don't know how to turn that into a formal, or this is part of the project, right? To try to turn that distribution, that training distribution, into a formal specification so we can then certify and we can monitor. And so the non-conformity measure of Xenophon was one of the technologies that's being developed. Let's see, so, and then JP talked, and from an aviation point of view, very realistic, right? It is not, and this is true across all the domains we spoke about today, it is not possible to list or model all possible things that could happen. So what do you do in real life? And he spoke about trust, which was again brought up in Dawn's talk. But trust. So you have fallback options, and you assess whether or not you have any remaining fallback options. So just being able to then take that and think about, how we might even formalize that is something that he and his group are working on, in particular in the particular landing problem where he's using stochastic reachable sets. And then finally, Dawn talked about trust. Her whole talk was about trust, developing and defining a taxonomy for calibrating trust. We're not used to doing that when we think about specifications, right? She sort of says, okay, in the good old engineering format for dynamic systems, can we take that framework and apply it to this new concept of trust, defining a dynamical model for understanding and updating trust? Okay, so I kind of put those together in this grand topic of specifications and certifying them. Let me just go through all of them and then we'll start our discussion. The second topic, I felt it was brought up a few times, namely in Daniela's talk and Sandeep's talk, but it's so important as we move forward because these neural nets are being used. I mean, computer vision has basically transformed, so it's all neural nets now, or 99.99% of it is using neural nets. So for camera-based perception in control loops, it's going to be using neural nets. So we saw some of that in Sandeep's talk. And in Daniela's talk, right? So she had a framework. Daniela introduced auditability. So how would you audit a neural net in a perception, as a perception module in a feedback loop, which is being used in autonomous cars? And so what Daniela did was she turned this huge, greater than 100,000 neuron end-to-end learning problem into something a lot smaller using a really clever idea, right? She turned the simple neurons into little ordinary differential equations. And then she was able to, in this, what's sort of inspired by the earthworm, the neural circuit policy, was able to replicate the behavior with this much smaller neural net, which one could understand, one could audit, and perhaps analyze. And then Sandeep, I mean, a lot of his program, the Assured Autonomy program, revolves around this idea of different ways to approach the problem of verification, simulation, and monitoring of neural nets in feedback control loops for the air domain, the ground domain, and the water domain. Okay, third category. I put these next two into two different categories because I think they're quite distinct. They're humans and automation. So the first of the two is modeling human behavior with and around a robot. And the second one is, how does the human perceive the automation? So they're kind of from two different points of view, and I think they're distinct enough that we should separate them. There were a bunch of different techniques. I pulled out a couple for each. So Daniela in her talk presented this idea of a single parameter. There were these two axes of, how do we model the humans around us? Well, let's do it on a reward tableau where in that 2 dimensions, you have reward to others and then reward to self. And then you use a single parameter theta to measure these different kinds of human behaviors, whether they be altruistic all the way through individualistic. So that's one parameter there. That's one way to model it. The cool thing is that it's a single parameter. So, in a high dimensional learning problem, maybe that, if you have a bunch of cars and you're trying to do this in a distributed way, if you only have one parameter, that's a really, that's a really valuable thing. And then, and JP in his talk, he introduced the concept of an autonomy quadrant. So I thought that was really a neat idea. So the quadrant here, again, the axes are the decision and the action. And he talked about autonomy. We really have to think about both the decision and the action. And in each of those, there was kind of whether the human's making the decision or the machine is making the decision. And for action, it's whether the human is taking the action or the machine is taking an action. So we can classify going from everywhere from non-autonomous operations to fully autonomous operations by asking, where are you in this 4-quadrant space? And then how do we how do we then kind of use this space to model human behavior with respect to the automation is quite interesting. Second topic with respect to humans that I think really came up in several places this morning, and I pulled out two, is how does the human perceive the automation? Okay, so Hadass in her talk, she said, what are the specification formalisms to capture this? How do we even start thinking about formal specifications when there's like when we're looking at safety specifications for human robot interaction? And then Dawn has talked about trust. So how do we build frameworks to estimate the trust that a person has of the automation? And then how do we calibrate it? In particular, she's interested in reducing trust miscalibrations. So not only do you want to make sure you don't trust it enough, but well, you want to make sure you trust it enough, but not too much. And Hadass brought this point out when she was talking about Todd Murphy's work in assisting but not over assisting. Okay, and then this one last question, and I kind of ran out of space on the slide, so I just put the question up, which is how can new technology help shape policy? I think this is something that, you know, every single talk is kind of, you know, pushing towards this. I think JP probably brought it up most. He sort of said it as this is one of his goals in the talk is to discuss this and think about how, you know, how we move towards shaping the policy in this new space of automation really being pushed into our daily lives in and around humans, so it has to be safe. But how do we there's kind of one school of thought that things are going too fast. Autonomous cars, they're there, we don't know if they're safe, but they're on the roads, you know, accidents are happening. Versus, you know, things are going too slowly. You know, some things it's to go through all of the kind of current way we certify systems is in real life is cumbersome. So how do we manage this in the future? And I think just this meeting that Gare and I are organizing with people from academia, industry, and government is a really great thing that we should not forget to talk about. And so that's there too. So with that summary, please, I'd like to open up the floor to, you know, what else are we missing here? What do people think? What are some thoughts about different topics? It's let's just start by opening it up. And we have, I think, until 50 minutes after the hour, right, Gare? That's kind of our, yeah, okay. So that's, we have a little bit of time now to discuss this.
Can I react to one thing that he said?
Yes, Hadass.
So you separated the modeling human behavior versus how the human perceive the automation. And I'm actually going to push a little bit back on the modeling human behavior because it's not really that we want to model the human behavior. What we want to model is the interaction, because humans are difficult. And, you know, and people spend a lot of time in creating different models. And I think the thing that Daniela talked about, again, not to speak for you, Daniela, but that one parameter, but it's really about the interaction itself, right? Who's going to get the right of way? It's not so much whether the person is altruistic or the person is sadistic. That was also on that that circle. But really, I think that conversation has to go a lot more towards modeling and verifying and specifying and whatever, maybe even synthesizing the interaction itself. And that is something that I'm not quite sure what it is yet, but I think we're starting to get a feel for what that looks like.
Yeah, Hadass, you're absolutely right. I think as opposed to saying modeling human behavior with and around robot, I think we should use the word interaction, because that we can't hope to do the whole behavior, right? It's very focused and problem specific, and that's where we should aim ourselves.
Yeah.
So Hadass, I would just say that the social value orientation parameter, the SVO, has been studied in a very different context by the social psychology community. And we took that parameter and we were able to incorporate it mathematically in the control function, in the cost function of a robot system. And so I just want to be clear that we have not invented social value orientation, but that on the other hand, social value orientation has been studied extensively as a way of modeling interaction between people. And so for our purposes, we have used it as a way of assessing whether you have a competitive or a helpful agent around you when you have to decide what to do next. And depending on whether you have competition or you have collaboration, you choose a different controller.
Yeah, but again, it's for that specific interaction. It's not,
Yeah.
not the person or the driver or whatever.
No, exactly. It's for the interaction. And so you can imagine how this notion of deciding the personality of the humans around the robot can be valuable in other contexts. But for us, the interest at the time of the work was focused on transportation. That's why we looked at those particular tasks.
Rujana, I saw your hand up.
Yes.
Hi, Rujana, how are you?
Okay. I have been sitting here and thinking from the old time. So here is one thing that I am missing in all these conversations, and I think it really brought back especially the presentation of Lars, where you really are dealing with real time, real time. And that brings me to the point that when you have a system that is so acutely dependent on real time, you have to be extremely careful how much data and how much measurement you are taking. And simplification comes into the foray. And from simplification, you go to these symbolic representation or some quantized representation. So here is what I am missing. I have been trying to understand this for the last month or so. There is a lot of effort from signal to symbol representation, but from symbol to signal representation is missing. And seems to me that that's what is absolutely needed when in real time you are simplifying the measurements, you make certain decisions, but then you need to correct it and you have to go back to the original measurement. That's all what I want to say. Any comments on that?
So you're saying, Rujana, that there's a lot of work on signal to symbol representation.
That's correct. Then
going from symbol back to signal.
That's correct. Absolutely correct. Yes.
Yeah. So how do we look at the kind of abstraction or the notation in the model maybe in a more abstract way, and then go back to what that really means for the real system?
And you have to do that, especially when you deal with airplanes and these very, very real-time systems.
I mean, in many ways, that's why in aviation, Rosanna, that we actually do a lot of so for the landing problem, the decision about what height you have to make a decision.
Yeah, Jean-Paul, you being an experienced man, you understand what I am after. What worries me is that in all this excitement about machine learning and neural nets and all the rest, they are all dependent on the fact that they are linear systems. And camera gives you, by definition, a linear representation of the data. Now, I work a lot with forces and torques and tactile data, which are by definition, by measurement system, are not give you immediately linear representation. So you have to be very careful what kind of extraction and simplification transformations you are applying on in order to simplify the system. But then when you have to correct your simplification, then you have to be able to go back to the data.
So I'd like to take Rujana's question and maybe ask both Jean-Paul and Lars, maybe in that order, to talk about a case maybe where you've used a simplification for JP, perhaps in the, you know, the example you presented, or another example in the aviation landing problem,
Yes, yes,
where you've
yes.
used a simplification and you've been able to do the design using that simplified model, and then you ran into a problem, or you found, or maybe it was just that worked because of certain things you designed into the problem to make sure the system, the actual system, was operating in the regimes, the simplified regimes that you've modeled. And I know Lars can speak to this too, because that was a key point in your talk, Lars,
Absolutely.
about how
Absolutely.
for the landing problem, you know, you use this convexification, but you were really strict about using this lossless convexification, so that you're able to kind of make sure that the operating space of the system is captured within, I mean, to some extent, right, within the model that you're using. And maybe some cases, I mean, we saw your initial tests, we saw the explosions. And I think there, you know, it goes back to JP's point, right? You can't capture everything. Things are going to happen that are outside even your modeling
Absolutely.
domain. But are there examples that the two of you can bring up of cases where you've had to maybe go to more complex models than you initially used, because this symbol to signal, this kind of abstract model to like real, or sorry, the simplified abstract model that you're using in design and in verification is just not, is not rich enough to capture the true dynamics?
So I will say not something that I have done, but it's something related to the landing problem. So as most people who work in aviation know, the instrument landing system was designed over 50 years ago. They're just basically a bunch of dipole antennas, dipole antenna arrays. And what you see happening is that we have this abstraction of there's a 90 megahertz and a 150 megahertz, and you look at the interpolation, the depth of deviation between those two. And that's basically what your glide slope is in one direction, and your localizer is basically 90 megahertz and 150 megahertz, right? And it goes all well. You line up on there and you measure the depth of modulation, and you tell how far you are from that center line. Now, it turns out that dipole antennas have this wonderful behavior, which they get reflective off of ground planes. And so we compensate for the ground plane, but if you have another airplane going by the antenna, or you have a truck going by the airport outside, they actually cause the glide slope and the localizer to wobble. So there's actually a case where you will, at some airports, depending on where the roadway is or where they hold the airplane, you can actually have reflections off the vertical fin of the airplane or the side of a big truck. And the actual waves wobble, and the airplanes will be coming into the runway wobbling down. So, so they actually had, I mean, that was something that, because they knew there was an abstraction, they had to actually, they restrict. And if you go to an airport and you'll see it, they will tell you, you can't go closer to the runway than this position. Because if you start, that will introduce nonlinearities in our propagation model, which will then mess up the airplane that's landing. So that's one case, that's one big case in the landing scheme, where your abstraction didn't quite work. And they learned it by experience, unfortunately, which is how we usually learn that our abstraction.
Actually, Jean-Paul, as you know, people are very good in readjusting and going back and looking again and feeling again. So people do this all the time.
Yep. But I wish we were able to have an automatic way of checking our abstractions in a more complex model as a way before we send things out. I mean, we do sensitivity analysis, but there's sensitivity if you have a linear model in a linear abstraction. They're not sensitivities to the nonlinearities of your system. And so I think that your point raised the interesting thing that we need to think about, which is, again, how do you measure your performance when you are out of the bounds? I mean, you have three options. Either you abort, which is what we typically do in aerospace. You design in something to deal with it, or you then, basically then compensate in some other way by changing your entire surroundings in which you operate. And so those are the sort of three things to deal with it. But we really don't have a way of saying, I've abstracted this, I've proven this, let me verify it in a non-abstracted space or a non-abstracted world. And I think that's a really good research area that we really need to think about.
Lars, do you have any thoughts to add to that?
Yeah, I mean, I think we end up in a really interesting chicken and egg situation. You know, I came from a control background where, you know, I would say, give me my model and give me my uncertainties, and I'll make sure that the system can be controlled. And then, you know, one of the great things about working at SpaceX is running into propulsion engineers, you know, literal rocket scientists. And I say, tell me how the rocket, how the engine's going to behave once it's been into space and back. And they say, yeah, that's great. Well, just go and do that, and then we'll tell you how it's going to behave. And then the same thing is true of the landing radar and things like that. So, you know, the point, actually, the main test objective of the flight we're doing tomorrow is to figure out what the aerodynamics are when you fly in this stalled configuration. And we've done wind tunnel testing on the ground, but it's at small scale, so we don't trust it completely. And we do CFD, so we don't entirely trust that. So I think functionally you end up in this really interesting situation where you come up with a model, you try and estimate uncertainties, which in itself is difficult, and then you have to rely on feedback in flight to try and mop up those errors. And if you get it wrong, I mean, it will be the end of the vehicle. And we've been able to fly enough times and fail enough times to learn where our uncertainties were not accurately capturing. And I'll share one story, which is that there was one flight where it became very apparent immediately that the rocket had no idea how high off the ground it was, off the drone ship, until the very last minute. And so basically it was blind, and then got very close to the drone ship, suddenly saw where the drone ship was, recomputed a trajectory, found one to the ground and landed. But afterwards we were just like, well, this radar has worked many times. Why didn't it work this time? And then eventually when we got the hardware back into port, the radar guys went out and took a look, and found that there's basically the radar box, and then there's the radar antenna, and then there's a cable that goes between the two, and that was completely severed. So there was just no connection between the box and the radar. I said, well, you know, you guys have definitely told me you need those antennas, right? Like, it definitely doesn't work without the antenna. And they said, well, actually that cord was working as an antenna, just one that would capture at 1/10 the altitude it was supposed to. And so it wasn't quite blind, you know, it was like nearly blind, but then as soon as it got close, like really close, it could see the ground, and that was enough. And that, you know, it's that kind of mysterious, you know, radio frequency stuff that I don't understand, but they swear blind that that's what happened. So, you know, next time we go and adjust our models for that.
Thank you, Lars. You really made my point. Wonderful.
Yeah, maybe this is connected. It's kind of a question that I thought of during Daniela's talk. Can you say something about, you know, transient performance when you're learning?
So what do you mean by transient performance?
Well, as you're getting data, you're learning, but you're also controlling. And I'm kind of trying to connect it to Lars kind of, you know, they have catastrophic failures sometimes while they're learning. But, you know, we could also have other types of bad failures. I'm just curious if you're, you know, how one quantifies those things, or how you bring, you know, deal with the uncertainty while you're learning.
Yeah, so let's see, we fully learn the policy before we deploy it on the actual vehicle. And so in our implementations, we don't change the model while the vehicle operates. Now we do a lot of experimentation and a lot of model changes and learning in simulation. And so over there, we keep track of all the potential crashes, and we improve. What else can I tell you? So we measure We measure the uncertainty. We actually have other research that is especially targeted at looking how the uncertainty in the data maps onto uncertainty in the model. And we have ways of assessing how the uncertainty in the data connects to the uncertainty in the model.
Hello.
How can we identify which data items need to be added to the data set in order to improve the performance? We do all this in simulation at the moment.
I see. So you kind of decouple the modeling from the policy generation in some sense, at least the scale on
we learn
it's sequential.
Yeah, sorry. So we learn the policy in simulation. The decoupling is between what we run on the actual platform and what we do in simulation. And part of the reason is that we are running this complex software on real cars, and we have some constraints over what it's okay for us to test on the car and what is not okay.
You know, that I always find that interesting because, you know, if you had a human, Daniela, and you'd say you're actually testing the human to see whether they will actually learn in a positive direction, as in they would always get better with each new experience, which is how you'd evaluate them. I mean, after a base level, you also evaluate this. So something like a derivative evaluation of their derivative in addition to the zeroth order. Yeah. And so I wonder if we can actually guarantee that derivative is the right direction.
For sure. So one thing I can say is that all the experimentation with the physical platforms collect data, but then that data is not used in real time at the time we collect it. It's used for training offline.
Right, but the question is, is there a way for us to guarantee the direction in which the training will go? I mean, that to me would be sort of pushing things into the next level.
Yeah, I mean, so for certain types of problems, we can look at the correlation between the uncertainty in the data, the uncertainty in the model, and we can do a feedback system where we can identify these are the portions of the data set that need to be enhanced with data, or this is how you might resample your data set in order to have certain properties that you might be interested in. For example, here is a visual example that I can explain to you in a few seconds. We can look at a data set of faces, and we can see where we have under representation, or where there is bias in that data set. And then we can create a method for resampling the data set to address that bias or that underrepresentation. And we can take the same idea and apply it for data sets for driving and for other domains.
So I'll maybe follow up on another question to Daniela. You showed in your talk that your system could handle the roundabout, which it had not been trained on. Now, I remember the first time I encountered a roundabout, it's like, oh, what is this? You know, but then you kind of it still follow the lane, right? So have you encountered any situations where your system could not handle the environment that it observed, that it had not been trained on? I'm just curious. I'm guessing there might be some good stories there.
Well, let's see. So I can tell you, Dawn, that at the moment, our system learns to steer according to the curvature of the road and according to the intersections of the road. And in the environments where we were able to test the system with the physical platforms, the system operated very well. I can't tell you that we covered all possible topologies and all possible scenarios. But we have seen some interesting crashes in simulation, for instance, right? So we have seen situations where we've introduced purposefully a lot of uncertainty, and we had various types of scenarios, primarily not in a static environment, but scenarios where we have other vehicles that move in the system, and those are much more challenging than the kind of static scenario, or almost static scenario that we have seen in the experiment so far.
Daniela, did you find that when you went to the simpler, or not the simpler, but the smaller neural network, did you find any degradation in performance?
No, actually, our paper, which is actually very, very fresh, the paper was published in October. So I told you almost everything that we already know about this. That paper actually shows that at least experimentally, the robustness tests we have done by doing something fairly simple, by looking at introducing increasingly more uncertainty in the data set used for training the end-to-end with 100,000 nodes and 500 million parameters, and the end-to-end with our system, and then a few other architectures. We have some charts that show you experimentally and empirically how the robustness it changes, but this is not by no means a rigorous and complete evaluation of robustness in the context of these systems. I think that there is a lot of opportunity for more extensive, more substantive approaches to assessing robustness. In fact, so for instance, we have not looked at all at what happens if you have an adversarial attack. We have not looked at the point of composition between the modules. So there's much work that still needs to be done there, and perhaps opportunities for collaborations.
Yeah, that sounds good. I know that Hadass has to leave in 2 or 3 minutes. She's leaving a few minutes early. So I wanted to just ask Hadass if she had any other comments or questions that she wanted to raise before she has to leave, or if we have any comments or questions for Hadass.
Yeah, I guess I have one that's kind of related to the question I discussed. You're using feedback in your setup, and sometimes we think about feedback as helping, right? It can help a lot, but it can also destabilize, in the usual setting, right? If there's too much uncertainty and the dynamics are not quite matched properly. Do you see any issues like that in your setup where you get the other edge of the feedback sword, the bad edge?
So the way we've been thinking mainly about feedback as a source of information to fix things. So the question is, what do you fix, right? So do you fix a specification? So can you add assumptions as you're going, or actually weaken assumptions? That's kind of one of the things we've been looking at in the past. It's not really intended. I'm not thinking about feedback as a closed loop, error signal that you're using to adjust your system, but rather as maybe the word better used is explanations, or explanations for what's going on that is problematic or could be problematic, right? So under these conditions, I might fail. Questions of falsification fall into that a little bit, or I can do this if this happens, but I cannot do it if this happens, right? So basically, taking advantage of the fact that we are explicitly stating what the system should do, so formal specifications, and being able from that to provide information about what the system can and cannot do based on those formal specifications. Because when you're writing, if I was to program some controller, typically the notion of specification is implicit. So maybe I have a requirements document, maybe I have, I used to work in a defense contractor before I went to grad school. There's these huge documents of what needs to be of these kind of either really, really, really detailed specifications, or there's some things that are just that you need to do, and they're not actually captured in any rigorous way necessarily. They're kind of in the hands of the designer. And I think my argument, or what I'm pushing, not just me, obviously, a lot of people are pushing to formalize the specification, because then we are able to reason about systems in a way that basically saying what the system can and cannot do, or what can we expect or not expect the system to do. So it really touches kind of on the things that Dawn showed. I don't know that I fully agree with the data as the specifications, Sandeep, sorry about that. But I mean, data is maybe what we have, but I don't think it's a specification necessarily. So yeah, so I think that's kind of where I'm coming from, the notion that we need to be we need to be very clear about what we expect our system or autonomy to do, and based on that, yeah.
So I guess I sort of stated that in the context of neural network, right? There is, for machine learning component, there is really no specification other than the data that you get, right? You may have that in, that is the problem, right? That's what I was alluding to, right? Now I want to ask, in this sort of feedback context, do you get contradictory specifications? So like, you may have started with some specification, then you get some feedback that's just completely contradicting what you have so far. And is there do you see sort of way to encounter that, address that?
So I think so here's the thing, right? And I think this kind of goes back a little bit to what Claire asked before. If I know to talk about it, it's easier for me to find solutions, right? So if I do get some contradictory specification along the way, maybe an assumption that I made has been violated. I'm running a runtime monitor and I see an assumption has been violated. Now, at least I have the knowledge to figure out what's the next, right? So next could be that I think I really liked JP's point of, am I going to fail, right? Is it the last failure? Are things going to go really, really bad later or not? So the ability to explicitly state what the system should be doing allows us to start mitigating these problems, right? So again, I think I don't think we can 100% assure every system. I just don't think we can do that, because these are physical systems, and maybe the cable between the box and the antenna got cut by something, right? So there's a bunch of things like that just, it's all a matter of increasing the assurance, I guess, if I was to use.
Hadas, I have a question for you before you go.
Okay.
Do you see a problem with over specification? And I say that from the aerospace experience, which is the very best aircraft that we have ever built. If you looked at the specification document that went from the DoD to the contractor, very, very, very clear. There's commander's intent, which I'm really a big fan of having on that, which is you have a clear statement of what your system should be able to, capabilities that it should have. But when we use the word what it should do, we often, because we're engineers and we have the engineer's disease, immediately go and tell you what the solution has to be and how you should implement something. And sometimes at the beginning, because you don't know, you over specify things that end up biting you somewhere else later. And so, I mean, in your work, have you seen the issue of overspecification? And my question is, how do you think we should handle that going forward?
So I think I've seen overspecification in the sense that mainly from the perspective of assumptions about the environment, specifying what the environment we think is going to look like. And then if the environment behaves differently, then I don't know, the system may or may not do things. So it's kind of, it's not so much that I overspecified such that there is no solution, but rather I overspecified such that I'm assuming a lot of things around me and they don't hold anymore, because we are talking about a physical system working in a physical space. And what do I do then, right? So the ability, but then we have the tools, right? We have the tools of runtime verification to check whether these specifications make sense anymore. We have the tools of any kind of consistency checking to see whether the specifications themselves, within themselves, are consistent. Do they make sense with the abstractions that I have? So I'm less concerned about over specifying, because that you can find out. You can find out that you've overspecified by the design space that you're left with.
But I've actually found that when things are overspecified in terms of our assumption about the environment, what usually happens is So the automation pulls up in hand and say, over to you, human.
Yeah.
And then we have low situational awareness and we end up in a bad situation. So that's the thing behind my question, which is, you know, what happens? Yes, you can say this one doesn't work or these three doesn't work, but then what to do next if these three don't work is always the question.
Yeah, these are all amazing questions. Yep, agreed. Okay, I'm really sorry.
I know you have to go, so I just wanted to make sure that we got our last questions in for you.
Yes, and just thank you so much. This has been a really phenomenal set of talks, and I really enjoyed it. So thank you very much.
Thank you for participating. Thanks for your wonderful talk.
Right.
I wonder if now's the right time, because we have about 15 minutes left, to talk a little bit about how new technology can help shape policy. I would like to spend some time on this, and I think it's incredibly important, and I think this is really the right place to talk about it in a workshop made up of the people who are here, because it's something that we've been it's something that I feel should have a more well-defined path than it does. I would say that from experience working in aviation, air traffic control, but also a little bit with flight carriers as well. And I wonder if I might ask JP to put you on the spot and maybe give a starting word about this, because you actually brought it up at the beginning of your talk. And maybe we can spend a few minutes now talking about this last point about technology and how like new technology, wherever it's developed, how can that shape policy, but how can it change the tools that are used, and how can that be adopted, or what are success examples? I'd also love to hear about the space, in the SpaceX case. What are the policies? Like, because there's sort of a lot of forging ahead in uncharted territory. So how does policy even get developed in those cases? So those are some of the thoughts that I'd like to spend a bit of time on now.
Yeah. So in my mind, engineering, policy, and law live in a circle, sort of a feedback system, where the job of the engineers is to define the art of the possible. The job of the policymakers is to define the art of the feasible. And then the job of the lawmakers is to define the what is reasonable, right? And so if you think about that, I think in engineering, we've in many ways not fulfilled that role as well as we have. We almost wait until the policymakers come to us and ask us, what should we do? But I think as we go through this, and I will tell you that AIAA has a committee, which I'm on, which we're actually doing this for autonomy in aviation, in aerospace, which is to try to figure out, in fact, that was the first meeting, one of the first meetings I had this morning, was trying to figure out how do we map the big questions that we have, so a lot of the things that we're talking about today, into policy questions, which is, how do we articulate the need for clear goals and objectives that can be then flowed down to whatever autonomy situation that you have, and having sort of a mantra of your autonomy must be able to do these things at a very sort of ethical, fundamental level that policymakers and the legal minds can say, okay, codify, that we can at the same time flow down to specific requirements for our.
So you mean us? When you say we, you mean engineers and
engineers? Yes, right. Yeah. So we need to develop the big things that we need to develop a mapping for, what does the technology enable us to do, right? And where are the issues where there room for ethical issues or other kind of issues where there needs to be discussion and clarification about what the thresholds are and what the boundaries are. I think that is where we need to make the connection. And And one of the things, for example, my past experience designing flight procedures, which is, we talk about RNAV and all this stuff that's happening now to change flight paths. I had a hand in the early days in making all that happen. And one of the things that has happened, and we talked about it back then, is the fact that we now can concentrate the aircraft trajectories so precisely that you now have an issue about whose house you fly these airplanes over, right? And so we have created a problem, which is a policy problem, by enabling technology. And so we need to be able to articulate those things. And autonomy will, that's just the way it is, create questions and issues for which you need clear policy. And I think we need to be able to, we call it on the committee, translate from engineer speak to policy speak, because that is something that we need to do early to avoid problems later
on.
Yeah, again,
maybe this is a,
go ahead, Dawn.
Can I ask maybe a silly question? So we have a process, like you mentioned, to give people pilot's licenses.
Yep.
And so would you think that there would be a similar process to give automation pilot's licenses to fly different types of aircraft in different conditions, or you think it should be a parallel or different process? I'm just curious. I think it's an interesting thing to give a driver's license to an automated vehicle that you can drive in certain.
Yep, no, it's a great question. And I do too. I actually think that you should. The question is, what we need to understand what people are testing for when they actually evaluate a human, right? And we talk about equivalent levels of safety. That's still a, you perform and you have 10 to the -9th and you have 10 to the -3, and this is better than that. But it's really, what are the things that you're testing for when you look at somebody and say, okay, I trust you to be able to drive on the road? I mean, mind you, I will probably say that over the years, I think that threshold has probably gone down, judging by the quality of driving on the road. But the fact of the matter is, we all look for something in the people we have to evaluate, whether it be grad students, your own children, or pilots. And I don't think we can articulate those well enough to be able to move to applying those to machines. But we need to, because clearly our history has shown that those are the things that have been proven to be successful, and those are the things that we really care about. And somehow we translate it from generation to generation and person to person, but I don't think we have a really way of articulating. So we need to figure that out, and that's part of the policy issue that I think clearly
right.
that we have to think about.
But it seems we have a much higher threshold for an automated system to drive a car or a plane than we would for a human, because we will tolerate human error, but we don't want to tolerate automation error.
Right. And I have a
anyways, I think it's, yeah, go ahead.
And I have a suspicion that in the end, we assume that the human is going to figure something out to save their own skin. And so we sort of have this sort of, buffer there that's like that amount of credit that we give them to compensate for things that we don't do for a machine.
Yeah, I'd just add to that. I think it's, to me, it appears sort of a bit dangerous to immediately associate sort of human-like qualities and apply the human-like decision criteria to autonomy, right? So when we assign a license to a pilot, well, we are certainly evaluating their piloting abilities, but implied in there is just an immense amount of sort of training and background knowledge that comes with the human, right? Which may be completely missing, right? So the decision making that goes into that whole process where a human pilot is operating or a human driver is operating, there's just a lot more there, and attributing sort of that level or that kind of characterization can introduce its own set of risks, and that's why sort of in my program, at least, we've put a little bit just more engineering perspective, right? And I think we just need to subject the autonomy to a little bit more rigorous scrutiny in some ways and limit it to the kind of sort of task that it is qualified for and capable of, I think.
Right, but Sandy, you know, one of the things is we have to distinguish between knowledge and decision making, because as you well know, every time we put up a machine against a human with terms of knowledge, like the Watson experiment with the the machine is going to win on knowledge, right? Because we can dump a lot of stuff in there and we can do a lot of analysis. It's how do you characterize decision-making ability, which is the thing that we have not been able to crack in terms of assessing machines. And we do it with humans, and I don't know how I do it, and I would love anybody on this call to tell me how they do it, but how do you assess the judgment of somebody that you're working with? If we can do that, then we're on a way to getting solution with machines.
Yeah, and I would even say that, you know, it's kind of, calling that machines have knowledge is probably more information, right, than knowledge. I think knowledge is still kind of sits one level above that. Yeah. So it's in the hierarchy, right, data, information, knowledge, and wisdom, right? And we associate sort of human with all these levels, but with machines, I think best is data and information, right, and being able to act on that information with the set of rules that we provide, rules or inference through examples in some ways, right? That's kind of the level that this is at. So coming from the sort of the safety perspective, I really push a little bit more on sort of providing more hardware assurance where we can, right? And putting sort of the guardrails from the operation monitoring perspective.
I'm not disagreeing with you, but I'm just saying that we need to figure out how to assess judgment, right? And assess people's ability to learn and get better like I was saying with Daniela, in one direction. If we can guarantee those things, then I think we'll be well on our way to dealing with machine autonomy in the fullest sense.
Can I ask Lars, we are running out of time, but Lars, can you say a few words about the, when you're, who are the organizations that you work with in terms of policies for the launches and for the space flights, and how do you find that, for example, SpaceX or maybe JPL or the organizations that you've worked with, how is the sort of that as JP put it, that the way engineers might actually have some influence on policy, how is that, what's your viewpoint of that?
Yeah, I should start by saying I feel far less qualified than JP or any other folks here to talk about policy, but I will try. We actually have a huge mishmash of organizations we deal with. So we deal with the FAA for launch licenses. We deal with the Air Force range when we use their facilities, and sometimes even when we don't use their facilities. And we deal with NASA when we're launching their payloads, or especially their people. And all of those will have different criteria, different processes. And I actually think navigating those can be some of our biggest challenges. We actually look to the airline industry or that world for inspiration, because I think we've lived in a world where space launches happen once every 2 months, 3 months, and you have a literal human sitting with their finger on a button to check whether the rocket is going off course and hitting the destruct button, where clearly, and the turnaround time for setting that all up is, submit things 60 days in advance for a single flight. And of course, there's no way that we can get to aircraft like, rates of flight with that kind of operations. And so going back to what some guys are saying about trust, we've actually pushed the range to allow us to use an autonomous system on board the rocket that is independent from the thing controlling the rocket, and only that unit has to go through the trust process with the range. But once they trust that unit, they can then go hands off. And the rocket itself is kind of like a thing sitting on the rocket, but the rocket itself is then trusted to say, I'm going off course, I'm doing something that's unsafe, and so I'm going to explode myself before I can go any further. So I think that there's definite progress there, and that has come from very much from us working with those agencies and saying, look, here are situations where we've been able to get to very high reliability and safety, such as in the aircraft industry, without having a huge amount of process and human in the loop type safety. So I think there's a long way to go, and we certainly try and, I don't know what right phrases, but we try and use the scientific method to say, yeah, I know the process is this currently, but does that really make sense given this data that we have now collected? And turning those gears can be difficult, but we make progress. And I think we have a clear idea of where we want to get to, and hopefully we can get there eventually. Yeah,
that sounds very reasonable. Okay, folks. So we are approaching, actually we're at 1:50, which is our end time for today. And I don't want to go on and go any longer than we suggested, but I do want to, and I'm going to pass it over to Gare in a second. I do want to thank all of our speakers for their just amazing talks, and all of our participants for just such an active participation, great questions. This discussion has been really great I know there's lots more, there's questions that have been in the chats that I've recorded that we haven't had a chance to answer. But I really appreciate everybody's engagement in this, and just one big thanks again to all of our speakers for their fabulous talks. And Gare, why don't you say a few words to end today and say something about tomorrow?
Yeah, so so thanks to all our speakers today for truly outstanding talks. And tomorrow we'll start again at 9 a.m. Pacific, with our first talk being Peter Abil tomorrow. So I hope to see everyone then. Good luck to Lars and SpaceX with their launch tomorrow. And again, thank you to everyone, and have a good evening, afternoon. Thank you.